Before this massive 300-meter steel Goliath ever hits the ocean, before it's even built in steel, it's built entirely in data. Just imagine a vessel so unimaginably huge that it can carry tens of thousands of tons of cargo across the world's most brutal, unforgiving environments. You don't just start welding pieces together and hope for the best, right? To construct a machine of that magnitude, you need absolute, undeniable precision. It's a fascinating, almost mind-bending journey from the virtual realm to physical reality, and in this explainer, we're going to see how that journey starts right here. This ship was built twice. First, in a computer. It's an incredible paradigm shift. We're way past the older days of enormous, echoing drafting halls with armies of draftsmen hunched over miles of paper blueprints. Today, every single heavy steel plate, every millimeter of highly pressurized pipe. Okay, let's dive into this. What we're talking about here is officially known as the ship product model. And by definition, it's a single, integrated 3D database containing every piece of information about the ship. Now, you have to understand this isn't just a basic 3D rendering or some high-end video game graphic meant to make a boardroom presentation look pretty. It's the absolute core engine of modern shipbuilding. It's an incredibly dense, highly technical digital twin that fundamentally dictates every single action the shipyard is going to take over the multi-year lifespan of the build. To truly grasp how complex this database is, we kind of have to visually deconstruct it layer by layer. When naval architects build this model, they're stacking distinct, highly intelligent systems. First, you've got your massive structural steel base, which is represented here in gray. Layered directly into that is your incredibly complex piping network in blue, moving fluids all over the vessel. Then the electrical cable trays snaking through every compartment in yellow, the HVAC ventilation ducts in green so the crew can actually breathe, and finally, all the remaining outfitting in orange. When you separate it out like this, you clearly see a densely layered, highly interactive environment where every single engineering discipline has to align perfectly. But hey, the visual geometry? That's really only half the story. The real power lies in what you can't immediately see. Every single object in this model carries heavy metadata. A piece of structural steel isn't just a gray rectangle. The database knows its exact material grade, its specific yield strength, and its center of gravity. For pipe runs, it continuously calculates the precise weight. For electrical trays, it holds the exact supplier and procurement information. And for major equipment, it tracks the strict class certification required by international maritime law. Functionally, this means the model doesn't just represent the ship. It fundamentally is the ship, captured entirely in code and data. All right, let's move right into Section 1, the chain reaction, driving downstream production. We'll see how this static data actually becomes a dynamic engine for the shipyard floor. Let's move to and see how this builds. How does all this data create a massive domino effect? Well, we start with the 3D model at step 1. When an engineer finalizes a specific hull section, the software automatically generates the precise 2D part geometry for every single frame and bracket at step 2. Those geometries are then automatically converted into numerical control or NC cutting tapes at step 3. These are the direct digital instructions sent to the robotic machines that will physically cut the steel. And finally, at step 4, this data drives the physical block assembly on the shop floor. The true beauty here is the connectivity. If an architect decides to change just one tiny dimension in the 3D model, that entire downstream flow updates completely automatically. And the outputs generated from this single model are incredibly diverse. The yard instantly gets highly detailed block assembly drawings tailored specifically for the welders. It produces incredibly precise material takeoff lists, meaning the procurement team knows exactly what raw materials and valves to order months in advance. It generates real-time weight reports as the design evolves, which feed directly back to the naval architects for critical stability and buoyancy checks. Because the software handles the translation directly from the 3D design to these 2D outputs, human transcription errors like misreading a crowded blueprint or typing the wrong number into a spreadsheet are entirely eliminated. It's a total game changer. And this brilliantly illustrates one of the most fascinating efficiencies in modern manufacturing, 94%. So what does that massive number represent? Well, when you directly link the computer-aided design to the manufacturing machines, the software automatically nests the individual part shapes onto standard flat steel plates. I want you to think of it like playing a very high-stakes, hyper-automated game of Tetris. The computer algorithm evaluates and arranges hundreds of oddly shaped pieces to achieve a 94% or higher usage of a single steel plate, rigorously minimizing any offcut waste. At the scale of shipbuilding, a tiny 1 or 2% improvement in this nesting process saves hundreds of tons of raw steel. It's a stunning display of efficiency, and it happens automatically, in seconds. Next up is Section 2, the high stakes, clash detection. I want you to imagine the sheer panic of realizing that a massive, rigid ventilation duct and a heavy, load-bearing structural beam have been accidentally designed to occupy the exact same physical space inside the ship's hull. That is exactly what clash detection prevents. It's the automated process of checking whether any structural member, pipe, duct, or cable tray physically collides with absolutely anything else. The software acts as this untiring supervisor, constantly scanning the millions of parts in the digital twin and instantly highlighting these physical collisions in bright red. An engineer simply sees the red warning, drags the virtual pipe a few centimeters out of the way, the red disappears, and you get a reassuring green checkmark. You're catching potentially catastrophic physical conflicts entirely in the digital realm. Now, what's really interesting about this slide is the stark real-world contrast in cost. Back in the days of managing thousands of paper drawings, clashes were almost always found down on the building berth, during the actual physical construction process. If you find a collision in the 3D model today, like we just said, it takes an engineer about 5 minutes of clicking and dragging to fix it forever. But if you find that exact same clash down on the berth, the consequences are severe. It means halting production lines, grabbing torches to physically rip out welded steel, throwing away expensive materials, rushing to reorder custom parts, and spending days to correct a single oversight. Literally thousands of dollars lost for just one single clash. So why does this matter so much? Because shipbuilding operates on a massive industrial scale, where delays cascade and profit margins can be extremely tight. A single ship might have tens of thousands of potential clash points. Finding and fixing these physical problems in the database before a single piece of steel is even cut is arguably the most valuable function of the digital twin. It fundamentally transforms the economics of the entire shipyard. Honestly, the software pays for itself many times over just by preventing these real-world disasters on the factory floor. So the crucial point is this. The ship product model is the single source of truth. It's the ultimate master guide for the entire lifespan of the build. From the massive steel hull structures all the way down to the smallest outfitting systems and piping brackets, everything must live in this central database first. It directly drives the manufacturing machines, it dictates exactly what procurement buys and when, and it establishes the absolute baseline for all downstream quality control. It's a true marvel of modern data management and heavy engineering. But all of this leaves us with an incredibly exciting, provocative question. As we've seen, the digital data is flawless. The nested steel is perfectly optimized to eliminate waste, and every single clash is completely resolved in the virtual world. But how do you actually turn those perfect pixels into 300 meters of raw floating steel? How do those automated machines physically cut, bend, and roll the heavy metal plates to match the code? That question bridges us directly from the brilliant concept of the digital twin into the gritty, heavy-duty reality of physical manufacturing. And with that, Section 1 is complete. Join us next time for Section 2, where we dive into procurement and actual steel preparation.